Today, in it is advanced time series analysis. By way of module objectives, by the end of this module, students should be able to understand why advanced time series models are needed beyond the ARIMA, describe and derive the ARC and GACH, estimate the ARC or GACH models conceptually, um, distinguish GACH variants, define co-integration formally, specify and estimate the VECM, use the Johansen framework conceptually, perform and interpret the VECM, then apply the ARC or GACH and VCM tools to realistic macroeconomic and financial examples and communicate the results. Now, introduction. Modern macroeconomics and financial data often display features that basic ARIMA style models cannot fully capture. Inflation and outputs can be linked through long-run equilibrium relationships, exchange rates, and prices may move together over decades, and financial returns exhibit volatility clustering, where periods of calm alternate with periods of turbulence. These patterns require models that separate short-run dynamics from long-run equilibrium adjustments, and that allow the variance of shorts to evolve over time. Advanced time series econometrics provide tools for these realities. Two major pillars are: one, volatility models, such as the ARC or GACH, which treat the conditional variance as time-varying and predictable from past information. Two, multivariate long-run models, such as integration and the vector error correction models, VECMs, which describe how non-stationary variables can share stable equilibrium relationship, even though each series trends over time. This module builds on earlier time series foundation, stationarity and unit test, the ARIMA modeling, and the concept of co-integration. We go deeper by deriving the core mechanics of the ARC or GAP estimation and diagnostics, and by presenting co-integration and VCMs modeling in a multivariate system framework that supports impulse response analysis and policy interpretation. Panel and cross-sectional econometrics often worry about heteroscedasticity as a nuisance. In finance and many micro settings, heterodacity is the object of interest. Risk and uncertainty fluctuate, and policy makers care about only the dynamics of volatility because it affects investments, exchange rates, pass-through, and financial stability. Why advanced time series model? Basic AMA or ARIMA models focus mainly on conditional mean, but many macro and financial datasets have two additional realities. Number one, uncertain changes over time. Two, variables change but remain tied together by long-run equilibrium forces, as co-integration. In finance, return may be nearly uncorrelated in levels, yet strongly uncorrelated in squared returns. Why in macroeconomics, inflation, money, exchange rates, and prices move together over long horizons, even when each series has a unit risk. Advanced models handle these realities by separating mean and variance dynamics, by using arch and gash, and by separating short-term from long-term equilibrium corrections. Looking at the key concepts and notations. Looking at conditional mean, this is the best forecast for YT, giving information up to T-1. Mean models include constant, AMA terms, regression with exogenous variables. Then, innovation shock. Once we fit the model, what remains unpredictable from this formula? Then we have conditional variance. Hard gas models treat as forecastable past shocks, and past variance help predict today's risk. For co-integration, a vector there exists better, such as this formula. That stationarity combines is the long-run equilibrium error. Let's look at the mean model versus the variance model. In volatility modeling, we first specify a mean equation, then model the variance of the residual shocks. This is crucial. Hash cash is about the conditional variance of T, E subscript T, not primarily about predicting the conditional mean. Then we have generic setup, where UT is the conditional mean model. If ZT is assumed abnormal, we have conditional normality. In practice, heavy tails are common. Even when distribution is misspecified, the Gaussian QML can remain consistent under mid regularities. Then this is the diagrammatic representation of the volatility clustering. This is the diagram. Then this is the diagram of the squared returns that are persistent. That is signature of the arc effect. This is how it looks like. Then let's look at arc properly. This is the equation for arc. Arc says today's volatility forecast rises when there are large shocks recently. Because shocks enter squared positive and negative surprises, they raise risk equally. Let's look at the parameters here, the meaning. This symbol here is the baseline variance. This here measures how strongly a shock periods ago rises against today's variance forecast. Arcs can fit volatility clustering, but often needs large Q to match persistency. This motivates GATCH, which introduced lagged variance to capture long memory parsimoniously. Let's look at GATCH. GATCH, this is the formula, this is the equation for deriving it. The GATCH add lagged variance terms. This makes volatility persistence, even with small q, because this particular part here, carries forward past volatility forecast. Interpretation in GATCH. Alpha is the short run using part. Then that is how much yesterday's shock moves today's risk. The beta is the persistency. How much yesterday's variance forecast carries into today. In many assets, alpha is modest, while the beta is large. Many shocks raise volatility, and volatility then decays slowly, matching real financial behaviors. Let's look at positivity, persistency, and mean reversion. This is the formula for it. If alpha plus beta is less than 1, volatility is mean reverting. After a shock, this part of the equation gradually returns to its long run level. If alpha plus beta is close to 1, volatility shocks decay very slowly. And all. Now this is the diagrammatic representation. Then we have quasi or maximum likelihood for GATCH. This is the very formula here. Then let's look at step-by-step conceptual estimation of GATCH. Step one, choose a mean model, estimate it, obtain residuals. If returns have no mean probability, then it may be a constant. Step 2, choose variance model and an innovation distribution. Step 3, for a parametric guess, recursively compute this. Step 4, compute log likelihood contributions using this and this, sum to this, then use numerical optimization subject to constraints. That means all of these parameters must be greater than 0 or equal to 0. Step 5, reports estimates, robust SC, persistency, alpha plus beta, then the implied long run variance. Let's look at diagnostics. 1, that ML. Before fixing GATCH, test whether residuals from the mean model shows ACT effect. The NJ ACT LM test, they ask, do lag squared residual help predict current squared results? The procedure is estimate the mean model, obtain residuals, then regress it on a constant and K lags. Then rejecting null hypothesis implies volatility is predictable from past shocks, especially the situation ACT and GATCH models are designed for. Diagnosis 2, standardized residuals across GATCH. After fitting the GATCH, Define standardized residuals as if the model captures volatility dynamics well. Then do practical steps. You plot it. If the squared standardized residuals remain autocorrelated, the variance model is specified. In applied work, do not judge a model only by the log likelihood. A good model should leave little structure in standardized residuals and should forecast volatility reasonably. Let's look at volatility forecast and long horizon convergence. This is the formula. Cash forecasting is one of the skills. The one-step forecast updates risk using yesterday's squared shock and yesterday's variance forecast. Now, this is the diagrammatic representation of the asymmetric volatility leverage. This is it here. Where you have your lag shocked, where you have your time minus one, yes minus one, here you have your next variable forecast. Now let's look at the asymmetric and persistent variance when the forecast is not enough. This is for this. This is catch adding an indicator. So negative shocks carry an extra effect. This is EGASH models, guaranteeing positivity without this constraint. Then choice is empirical plus economical. Let's look at a worked example, exchange rate return. Define the daily exchange rate return, then do your workflow, then carry out policy interpretation. Let's look at the spurious regression problem. Why quantification exists. If Y subscript T and S subscript T are independent independent random walks, regressing in levels can yield a higher R squared and significant T statistics, even though there is no true relationship. There's a statistical illusion caused by the training behavior. The mechanism is this. OLS assume residuals as stationary, but quantification resolves this. It asks whether a particular linear combination of training variables is stationary, indicating a stable long-run equilibrium relationship. This is the grammatic representation. When you have your levels here and you have it measuring against T, this is the diagram. Then let's have the formal definition of cointegration. In this is the formula for it. This is cointegrating vector. Why this is the cointegration error here? This is what cointegration means. The economic meaning. The variable may wander in the short run, but their force is pulling them back to equilibrium because the deviation beta S subscript T does not drift away. Now, this is the diagrammatic representation of cointegration error. Mean can be stationary, even if the level trends. This is cointegration error here. This is time. Then this is the diagram for error correction intuition. That is mean reversion in disequilibrium. This is what it looks like. Equilibrium deviation against time. Then we have two variable, that is VCM illustration interpretation. This is a practical illustration here. Then let's look at what the Johansen framework is talking about. Why we need it in multivariate system. Angel Granger is useful for a single cointegration relation, but has limitations. Johansen treats this system jointly in a batch or BCM framework and estimate both the arrow and the beta vectors via reduced rank regression. It is the standard approach which supports multiple equilibria among several I1 variables. Practical steps: do your unit root checks, carry out VRA relaxation, choose deterministic Johansen, and estimate the alpha plus beta. Let's look at Johansen rank test. Number one, trace test. Do the max Eigen test. Then, in practice, you often report both. Check robustness across lags and deterministic cases. Then choose arrow based on statistical evidence and economic possibility. A statistically undefined beta that is economically nonsensical is not helpful. Let's look at diagnostic and practical caution in VCM. Length lag. Too many lags waste degrees of freedom. Too few lags leave serial correlation. Deterministic term. We have structural breaks. We have residual issues. Now let's look at impulse response, ROF, and VED in co-integrated systems. A VCM can be converted to a VAR representation to compute impulse response functions. The part of each variable after one shock. Now, forecast error variance decomposition. Ask, at horizon K, what fraction of the forecast error variance is explained by shock to variable J? This is useful for policy, e.g., how much inflation or sensitivity is driven by exchange rate shock. Now, let's look at an example, the PP and adjustment burden conceptually. So consider nominal exchange rate of this, foreign exchange price of this. PP suggests that this part of the equation should be stationary. If the one saying arrow indicates 1, we normalize beta on E subscript T and interpret the long run relation as subscript T is equals to PT. Adjustment alpha, textbook corrects PPT and all. Let's look at the policy relevance. If PPT deviations correct mainly through the exchange rate, the exchange rate shock can dominate inflation dynamics via pass-through. By way of conclusion, advanced time series econometrics expands our ability to model two central realities of economic data: volatility that changes over time and long-run relationship among trendy variables. ACT and GAT model treat conditional variance as a dynamic process, capturing volatility and enabling volatility forecast. Beyond the basic GAT workouts, asymmetric specification accounts for leverage effects and provide richer description of risk. Co-integration and VCM provide a coherent framework for modeling non-stationary macroeconomic variables that nevertheless move together. In applied work, all these tools must be used responsibly. Test for unit roots and breaks. Choose lags structures carefully. Check residual diagnostics. Interpret results economically rather than mechanically. When well done, advanced time series method prove useful evidence for understanding risk, persistency, and long-run macroeconomic structure. That will be all for Module 8. See you in July.